Today I will show you how computers can do simple math with just zeros and ones and what can go wrong. I'll show you how binary addition and subtraction works, and then briefly touch on the topic of representing negative numbers. Understanding binary is key to understanding how computers store and process data, and even how they can fail. Hey, my name is Oliver, and I am a final year computer science bachelor student. When I started off my studies, I had some difficulties with some of the basics of computer science, but since then I have found ways to simplify the concepts for myself, and now feel quite confident in my abilities. I hope to make some of these concepts more accessible through my videos. If you do not know what binary numbers are yet, I suggest you watch my first video on binary numbers before watching this one to get a better understanding. By the end of this video, you'll be able to solve questions such as these, where we're adding or subtracting two binary numbers. We're going to be working on these two examples, and we're going to start off by converting these into decimal, or rather, I have this conversion here, and I suggest, if you're still not super comfortable with working with binary numbers, to use my previous video to do some of these conversions so you get some practice in. So first, we're just going to do this addition in decimal. So I'll write as one would usually write it, 13 over 7, and then write this little plus. What you would then do in decimal representation is add these two numbers, and notice we get 3 plus 7 is 10. And in our lower value position, we have a 0, which we write directly underneath these two digits. But then we have a value that's carried over, this 1. And this 1 goes over here above our 10 position. So the position that's responsible for the 10s. And then we add up this column to get the 10 position here. So 1 plus 1 is 2, and our solution is 20. Decimal representation. The way this is done in binary is actually quite similar. The only difference we have is instead of adding up to 10 in each of these rows or columns, we do it to 2. So where we would be doing for decimal up to 10 as written in the 10, we would be doing it for binary to the 2. So let's start by writing both of these numbers and their representation above each other. So 1, 1, 0, 1, and then underneath 0, 1, 1, 1. And then we'll go ahead by applying this format as we did before here, but this time with 2s. So we have our two 1s here, and we know that 1 plus 1 is 2. Now 2 we can't represent, so we would treat it as a carry. So in our case, 1 plus 1 in binary representation would be equal to 1, 0 in binary representation, as we cannot store the digit 2 here, and it needs to be carried over to the next position. So what happens in this column is that this lower value position goes here, and our carry value goes to the next highest value. So we write our 0 here, and our 1 gets carried up here, and then we do the same again. We add this column, and this time we have the same case where we have 1 plus 1 is 2. So we write our lower value down here, our carry goes up here, and we go again. This time we have 1 plus 1 plus 1. So this time we have the binary representation of 3, which is 1, 1. So we have a carry of 1 and also a remainder of 1. So this here, the lower value, we move down here once more, and the carry goes up here as before. So this time, instead of writing 0, we write 1, and the carry is also 1, and then we continue on. This time, our column again has two 1s, so we know in this case that we have a carry of 1 and a remainder of 0. One last time, we just have the carry in this case, so we add up 1 plus, and we have here implicitly, so without it standing there, we know that this is a 0. Add these two up, and we get 1 without a carry. And then write, for clarity, this 2. So this now is our result. 1, 0, 1, 0, 0. If we convert this to decimal, and I'll do this real quick. So we know this is value 1, 2, 4, 8, 16. So it's 16 plus 4, which is 20. And this is exactly what we saw here. So we know that this calculation is correct. Now, as you may have noticed, we had two binary numbers using 4 digits each, and we got out a binary number that uses 5 digits. This, for our calculation, is not an issue, but for computers, we have to limit, or we have to define exactly how many positions each number takes. So, for example, if during this calculations we say, yes, we just need 4 values, but then end up calculating this, so requiring one more position than we have available, the computer representation actually just cuts off this highest bit. So the number we're left with will actually just be 4. And this is what's called an overflow in computers, and these can become irrelevant or problematic if not considered. But as I just wanted to mention this briefly, I will not discuss this much more deeply. Now, moving on to our subtraction, we're gonna do the same as with decimal numbers. So first with decimal numbers, here 13 minus our 7. If you're familiar with subtractions, you'll know that what we do is we'll try to subtract 7 from 3, but notice that 3 is smaller than 7, so we'll need to borrow this one here for a 3. So I'll write this one here, cross out this 1 and subtract 1, so we get 0, and then do 13 minus 7. Now, this might not actually help, but I assume you're familiar with decimal subtraction, so this is just to refresh how this is done more or less. What we actually get out of this in the end will be 6, and we'll just copy this format for working with binary numbers. So I will copy these binary numbers we worked with before, and then write the minus in front. So what we'll do here is we have this one up here, and we're subtracting 1, so we'll get 0. Moving on, we'll be trying to subtract 1 from 0. So we notice, yeah, this is not possible. We'll need to borrow from the next highest value. So we cross this out, and this becomes 0. And then we have this borrowed 1. So 1, 0 in binary representation means 2. And then subtracting 1 off it, we'll get 1. So it will be 1 down here. So I'll write this just on the side. And then moving on to the next one, we'll again be trying to subtract 1 from 0, which requires us to borrow from this 1 once more. So we cross this out, get our 0, and then up here have the borrowed 1, and do the same addition. So we know that 1, 0 in binary representation minus 1 in binary representation is 1, and then we move on. For our next case, we're subtracting 0, which means that we're not taking anything away, and we can just get the value that's up here. So 0 minus 0 is just 0. So this is then our results, and this number is, if we calculate, if we do our conversion again, here's 1, 2, 4, 8. So it would be 4 plus 2, which is 6 in decimal representation. And then if we look up here, we see it's also 6. So the subtraction also worked. Now, what if we actually try to subtract a number that's bigger from a number that's smaller? So if we did this subtraction we just did, but in reverse. So this here minus this. Now what you'll notice here, I'll just skip over these numbers as the relevant part is here, is we'll try to subtract 1 from 0, which would normally require us to borrow, but we don't have any 1 in front here which we can borrow from. Now this would be called an underflow, and is also a type of issue that can happen in arithmetic from computers. One of the ways, at least this specific case of underflow, one of the ways to combat this is to introduce negative numbers. So currently, we only know how to present or represent positive numbers. So to be able to properly represent this subtraction here, we would have to use a negative sign. One way to do this, at least on paper, is just to switch these two values, and then in the result, adding a negative in front. So in our case, switching these two values would result in this same subtraction. So we know that the result would be this, except that now we would add a minus in front. So our result would be 0, 1, 1, 0 with a negative in front. So it just would be negative 6. However, in computers, we don't really have a way to represent this negative, at least not as a negative, in one bit. The way this is done is usually with another bit, so either a 0 or a 1, which would represent whether this number is positive or negative. This would, for example, be if the first bit is a 1, then the numbers that follow afterwards would be negative. So this would then be split into this, which would represent the number, and this that would represent the sign. So this one sign, and this one number. A better way for computers to work with negative numbers is something called 2's complement. And I will get into this at a later point, but essentially this allows us to do addition the way we've done it before without switching around the order of subtraction and still work with negative numbers. If you enjoyed this video, subscribe for more computer science content and let me know whether there are any specific topics you would like me to cover next.